Welcome back to Understanding Quantum Information and Computation. My name is John Watrous, and I'm the Technical Director for Education at IBM Quantum. This is the 13th lesson of the series, and it's the first lesson in the fourth and final unit, which is on quantum error correction. Quantum computing has the potential to enable efficient solutions to computational tasks for which efficient classical algorithms are not known and possibly don't exist. There are, however, very significant challenges that will need to be overcome if we're to implement the sorts of large-scale quantum computations that we hope will one day be possible. The heart of the matter is that quantum information is extremely fragile. You can literally ruin it just by looking at it. And so, to operate correctly, quantum computers need to isolate the quantum information they store from the environment around them to an extreme degree. But at the same time, the quantum computer itself must provide us with very precise control over this quantum information, and that includes proper initialization, accurate and reliable unitary operations, and of course the ability to perform measurements so that we can actually obtain the results of the computation. There's clearly some tension between these requirements, and in the early days of quantum computing, there were some who viewed that the fragility of quantum information and its susceptibility to both inaccuracies and environmental noise would ultimately make quantum computing impossible. Today, there's little doubt that building an accurate and reliable large-scale quantum computer is a monumental challenge. But we have a key tool to help us in this endeavor that leads most people who are knowledgeable about the field to be optimistic about large-scale quantum computing one day becoming a reality. And that tool is quantum error correction. For the next 4 lessons, we'll discuss quantum error correction with a focus on the fundamentals. In this lesson, we'll take a first look at quantum error correction, including one of the very first quantum error correcting codes discovered, the 9-qubit Shor code. And we'll also discuss another fundamental concept in quantum error correction, which is known as the discretization of errors. In the subsequent lessons of the unit, we'll see more sophisticated and ultimately better quantum error correcting code constructions, and we'll also discuss the problem of quantum computation on encoded quantum information using computational components that are themselves not perfect and prone to errors. Here's a brief overview of the lesson. We'll begin by discussing classical repetition codes, which are perhaps the simplest and most basic type of classical error correcting code. Classical repetition codes aren't particularly good codes by classical coding theory standards, at least on their own, but that's okay. Here we're going for simplicity. And in particular, we'll take a look at just about the simplest classical error correcting code you can possibly imagine, which we'll then use as a basis for a simple example of a quantum error correcting code. That example is the 9-qubit Shor code, which we'll discuss in detail, including a description of the code itself, as well as procedures for encoding qubits using this code, detecting errors on encoded qubits, and correcting those errors. And in the third part of the lesson, we'll discuss the discretization of errors, which allows us to think about arbitrary errors on qubits, which in principle form a continuum of possibilities in discrete terms, essentially boiling errors down to so-called bit flips and phase flips. Before we get into the technical details of quantum error correction, it's worth taking just a moment to consider the need for quantum error correction, as well as classical error correction. As I suggested at the start of the lesson, quantum computers are highly susceptible to errors, owing to the fragility of quantum information. In particular, unwanted interactions with the environment, or in other words, the rest of the world, can disturb quantum information. These unwanted interactions can cause decoherence, where information essentially leaks into the environment, causing the information stored by the quantum computer to behave more and more classically. It's also critically important that we recognize that quantum operations can only be performed with limited accuracy. For example, we might wish to perform a particular quantum gate on a qubit, but because physical devices are never perfect, what we actually implement might be just an approximation to that gate. That might not be a big deal for a single gate, but if our intention is to perform thousands or millions of quantum gates, these small inaccuracies will start to accrue. And when the computation is finished, we could end up with a very different state from what we expected. So this is a rather different source of errors, but it's certainly one that we can't ignore. People have been studying classical error correcting codes for close to a century, and these codes have many applications, including in information transmission and storage. But because classical computing components are so reliable, we don't actually need error correction to build classical computers. Now, it might be the case that error correction isn't actually needed to build reliable large-scale quantum computers either. For example, the main idea behind topological quantum computing is that it might be possible to build robust quantum systems that are inherently protected against noise due to topological properties of the systems. But we don't know if this will be possible, and it's pretty widely believed that error correction will probably be essential in one form or another for large-scale quantum computing. Now we'll discuss classical repetition codes, which form the basis for our first quantum error correcting code, the 9-qubit Shor code, which we'll see shortly. Repetition codes are extremely basic examples of error correcting codes. The idea is that we can protect bits against errors by simply repeating each bit some number of times. In particular, let's take a look at the 3-bit repetition code. Here we encode one bit into 3 by simply repeating the bit 3 times. So 0 is encoded as 000, and 1 is encoded as 111. Of course, if nothing goes wrong, we can easily distinguish the two possibilities. But if there was an error and one of the bits flipped, let's say, meaning that a 0 changes into a 1 or a 1 changes into a 0, then we can still figure out what the original bit was by seeing which of the two binary values appears twice. Equivalently, we can decode by computing the majority value, or in other words, the binary value that appears most frequently. And it's not hard to see that if we have at most one bit flip error, then the decoding will be correct. Of course, if 2 bits flip, or if all 3 bits flip, then it won't work, and we'll get the wrong value when we decode. And that's a general property that every error correcting code possesses. You may be able to correct some errors, but you'll never be able to correct every error, and ultimately it's about decreasing the chance of an error as opposed to guaranteeing correctness, which is generally not possible. As an example of a situation in which we can decrease the chance of making an error, let's suppose that our goal is to communicate a single bit to a hypothetical receiver. And to do this, we're able to transmit bits through a so-called binary symmetric channel, which flips each bit sent through it independently with some probability p. So with probability 1 minus p, the receiver will get whichever bit we intended to send, but with probability p, the bit flips, and the receiver gets the opposite value to whatever we sent. So if we don't use the repetition code, and instead we just send whatever bit we have in mind through the channel, the receiver will get the wrong bit with probability p. On the other hand, if we first encode the bit we want to send using the 3-bit repetition code, and then send each of the 3 bits of the encoding through the channel, then each one of them flips with probability p. So the chances of a bit flip are now greater because there are now 3 bits that could possibly flip rather than 1, but if at most one of the bits flips, then the receiver will be able to correctly decode. So we'll only get an error after decoding if 2 or more of the bits flip during transmission. And it's not too hard to calculate that this happens with probability 3 times p squared minus 2 times p cubed. For values of p smaller than 1/2, this leads to a decrease in the probability that the receiver ends up with the wrong bit. There will still be a chance of an error in this case, but the code decreases the likelihood of this. And if you wanted to decrease the chance even further, you could do that using a different code, including but not limited to the possibility of using a repetition code where the encoded bit is repeated more than 3 times. For values of p greater than 1/2, by the way, the code actually makes things worse, in the sense that it increases the likelihood that the receiver gets the wrong bit. So we would certainly not use this code in that situation. The 3-bit repetition code is a classical error correcting code, but we can also consider what happens if we try to use it to protect qubits against errors. It's not a very good quantum error correcting code, as we'll see. It can correct against some errors, but it makes other errors more likely. It is, however, the first step toward the Shor code, so let's see how it works for qubits. First, to be clear, when we refer to the 3-bit repetition code being used for qubits, what we have in mind is an encoding of a qubit as is shown on the screen, where alpha 0 plus beta 1 is encoded as alpha 000 plus beta 111, or in other words, the standard basis state is repeated 3 times. Notice in particular that this is not the same thing as repeating the quantum state 3 times, as in a given quantum state psi being encoded as psi tensor psi tensor psi, which is not an encoding that we would be able to implement for an unknown quantum state psi by the no-cloning theorem. The encoding that we're talking about, on the other hand, is very easily implemented. Here's a very simple quantum circuit that does it using 2 initialized workspace qubits and 2 controlled NOT gates. Now let's suppose that an error takes place after the encoding has been performed, and in particular, let's suppose that a poly X operation, or in other words, a bit flip, happens on one of the qubits, and in this figure, it's the middle qubit. Of course, this isn't the only sort of error that could occur, and you might object to the idea that an error takes the form of this perfect unitary operation, but we'll come back to this later in the lesson, and for now, we can just think about it as an example. Here's the resulting state. It's the same as the original encoding, except that the middle bit within each ket has been flipped. Obviously, we can see this from the mathematical expressions for the state, but suppose that we only had the 3 qubits, and that we suspected that a bit flip might have occurred, but we didn't know which qubit might have been affected. One way to figure out if a bit flip occurred would be to perform a standard basis measurement and examine the outcome. In this case, we would see either 010 or 101, with probabilities depending on alpha and beta, and in either case, our conclusion would be that the middle bit flipped. But unfortunately, that ruins the original quantum state, and this state might be precious to us. After all, the whole point is to protect this quantum state, so this is not a good option. What we can do instead is to use the quantum circuit shown here on the screen, where we feed the encoded state into the top 3 qubits. Basically, what this circuit does is to compute the parity of the standard basis states for the top 2 qubits as well as for the bottom 2 qubits of the encoding, and this will reveal the location of the bit flip. In particular, in this case, we'll get the outcome 1 for both of these parity checks, and from that information, we can conclude that it's the middle bit that's different from the other 2, so that's evidently the one that flipped. And crucially, this does not cause the state to collapse. So we now have a chance to try to correct this bit flip so that eventually we can perhaps decode and get our original state back. We'll come back to the correction in a moment, but first let's briefly consider the other possibilities for a bit flip error. If instead the bit flip error occurred on the bottom or leftmost qubit, then we would get the outcome 10, reading from bottom to top, and again the state wouldn't change. And if the bit flip happened to the top qubit, then the output would be 01, and once again the state doesn't change. And by the way, if there was no bit flip error at all, then the measurement outcome is 00, and once again the state comes out unchanged. So let's summarize all this in the form of a table, where we list each of the possible states that we obtain from at most one bit flip, the measurement outcomes, which we refer to as the syndrome in the context of error correction, and the correction we need to make in order to get the original encoding back. If there was no error, the syndrome is 00, and nothing needs to be done to fix the state. If the bottom or leftmost qubit experienced a bit flip, the syndrome is 10, and the appropriate correction is to apply an X gate to the bottom or leftmost qubit. And the other 2 cases are similar. So, if we apply the appropriate correction based on the syndrome, then we'll be certain to recover the original encoding in all 4 cases. Once again, we're only considering the possibility that at most one bit flip error occurred. This wouldn't work correctly if 2 or 3 bits flipped, and we also haven't considered the possibility of other errors. Now let's consider a different type of error. In the quantum setting, bit flip errors aren't the only errors that we need to worry about. For instance, we also have to worry about phase flip errors, or just phase flips for short, which are described by Z-gates, or equivalently, poly-Z operations. Unfortunately, the 3-bit repetition code completely fails to detect phase flips. For instance, supposing that we encode a qubit using the 3-bit repetition code just like before, and a phase flip error occurs on the middle qubit, we'll obtain the state that's shown on the screen, which is exactly the encoding that we would have gotten if a phase flip had happened to the original qubit before we encoded. And so, if we perform the same circuit as before to try to detect an error, we would get the syndrome 00, which wrongly suggests that no errors took place. So the 3-bit repetition code works for at most 1 bit flip error, but it fails to detect phase flip errors. In fact, it actually makes things worse in some sense, because now we have 3 times as many qubits that could potentially experience phase flip errors. We've observed that the 3-bit repetition code is completely oblivious to phase flip errors, so it doesn't seem to be very helpful for dealing with this sort of error. But in fact, we can modify the 3-bit repetition code so that it does detect phase flip errors, and I'll explain now how this can be done. Here's the original circuit for encoding a qubit using the 3-bit repetition code, and the way that we'll modify it is very simple. We just apply a Hadamard gate to each qubit of the encoding. A Hadamard gate transforms a 0 state into a plus state and a 1 state into a minus state, so the net effect is that we obtain the state that's shown on the screen, where ket plus 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 and ket minus 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 are shorthand notation for the tensor product of 3 plus states or 3 minus states. A phase flip error, or in other words a z-gate, transforms plus states into minus states and minus states into plus states, so this encoding will be useful for detecting and correcting phase flip errors. And to do that, we can modify the error detection circuit from before in the following way. Here's the circuit from before, and what we'll do is simply to put Hadamard gates at both the beginning and the end as is shown on the screen. The idea is very simple. The first 3 Hadamard gates transform plus and minus states back into 0 and 1 states. The same parity checks as before take place, and then the second layer of Hadamard gates brings us back to our encoding. Another way of thinking about this is that we're basically just transforming phase flip errors into bit flip errors by conjugating by Hadamard operations. We can, by the way, simplify the circuit just a little bit. This circuit here is completely equivalent, and you can check this for yourself if you're so inclined. So, if we put our encoded qubit into this circuit, assuming no phase flip errors have occurred, we get the syndrome 00, indicating that there were no phase flip errors. And if we do have a phase flip error on the top qubit, let's say, then the rightmost pluses and minuses flip, and that results in a different error syndrome, 01 in this case. That identifies the location of the phase flip, just like we had for bit flips, and we can then correct it by applying a z-gate to the top qubit. And the situation is similar for phase flip errors on either of the other 2 qubits. So we can in fact detect and correct up to 1 phase flip error using this code, but unfortunately, as you may have guessed, we can now no longer correct bit flip errors. All is not lost, however, because we can in fact combine these 2 codes together to obtain a code that can correct both bit flip and phase flip errors, and in fact it will be able to correct for any error on a single qubit. It's now time to discuss the 9-qubit Shor code, which is a quantum error correcting code that we can obtain by combining together the 2 codes that we just saw, meaning the 3-bit repetition code that allows us to correct a single bit flip error, and the modified version of that code that allows us to correct a single phase flip error. To be more precise, the 9-qubit Shor code is the code that we obtain by concatenating the 2 codes, which means that we first apply one encoding, which encodes 1 qubit into 3, and then we apply the other encoding to each of the 3 qubits separately, so we'll get 9 qubits in total. We can express this in the form of a circuit diagram as follows. First, we'll apply the modified version of the 3-bit repetition code that detects phase flip errors, and then we'll encode each of the resulting qubits independently using the original 3-bit repetition code. So if we shrink this circuit down just a little bit to make some more room, we can specify the code in somewhat different terms by describing how the 2 standard basis states for our original qubit get encoded. And once we know this, we can determine by linearity how an arbitrary qubit state vector gets encoded. So that is the 9-qubit Shor code, and the idea is that one of the codes allows us to correct phase flip errors, and the other code allows us to correct bit flip errors, and as we'll see, that will in fact imply that we can correct an arbitrary error on a single qubit. Now let's see how we can detect and correct errors using the 9-qubit Shor code, starting with bit flip errors, which are also called X errors. Here's the circuit that performs the encoding, and just to make it easier to talk about, we'll think about the 9 qubits we get from this code as being grouped into 3 blocks of 3 qubits, where each block represents the encoding that we get from applying the second encoding step, which is the ordinary 3-bit repetition code. That's called the inner code in this context, whereas the outer code is the code used for the first encoding step, which in this case is the modified version of the 3-bit repetition code that works for phase flip errors. To correct bit flip errors, we can simply treat each of the blocks separately. Each block is an encoding of a qubit using the 3-bit repetition code, and that code protects against bit flip errors. Suppose first that an X error occurs on any one of the qubits, such as the middle qubit in the middle block. If we independently check each of the blocks for bit flip errors and correct for any errors we find, then this error will be corrected and the original encoding will be recovered. In fact, we could even have multiple X errors and still correct them in this way, provided that the errors are in separate blocks. If we had 2 or 3 X errors in a single block, we'd be in trouble, but as long as there's at most 1 X error per block, the inner code will catch them and we'll be able to recover the original encoded state. So, correcting bit flip errors is a pretty simple matter for this code. We also need to consider phase flip errors, or in other words, Z errors. This time it's not quite so clear what we should do because the outer code is the one that corrects for phase flip errors, but we can't directly detect and correct them because the inner code is somehow in the way, but we'll see how to do this shortly. To better understand how X and Z errors work and the effects that they have within quantum circuits, it's helpful to observe a few simple relationships between these errors and CNOT gates, and this will also be helpful in a later lesson. First, let's start with X errors, or X gates, and how they relate to CNOT gates. If we apply an X gate to the target qubit of a CNOT, and then apply the CNOT, then that's equivalent to swapping the order and doing the CNOT first. On the other hand, if we apply an X gate to the control qubit of a CNOT, and then apply the CNOT, we can't simply switch the order, but instead we have to apply the X gate to both qubits, and you can check all of these relationships on your own if you wish, by thinking about what happens to standard basis states, for instance. The situation is similar for Z errors, except that the roles of the control and target qubits switches. In particular, if we perform a Z gate on the control qubit of a CNOT, and then perform the CNOT, then that has the same effect as performing the Z gate after the CNOT. But if we perform the Z gate on the target qubit instead, then that's equivalent to first performing the CNOT and then applying a Z gate to both qubits. And finally, all of these relationships are symmetric in the sense that we can always swap the ordering of the gates on both sides of each equation, which is equivalent to taking the inverse or the conjugate transpose of both sides, given that X, Z, and CNOT gates are all their own inverses. Now let's consider phase flip errors and how we can detect and correct them using the 9-qubit Shor code. Here's our encoding circuit, and we'll continue to think about the 9 qubits used in the encoding as being grouped into 3 blocks of 3 qubits. Suppose that a Z error occurs on any one of the qubits, such as the one indicated here. Using what we just observed about Z gates and CNOT gates, that's equivalent to 2 Z errors prior to the CNOT, one on the control and one on the target qubit. And these errors happen to commute with the other CNOT in the block, so we can swap the ordering, and here's what we obtain. The lower Z error doesn't do anything because it's acting on a 0 state, and we can slide everything else over and obtain this diagram. So what we found is that a Z error somewhere within the middle block is equivalent to a Z error occurring on the middle qubit prior to the second encoding phase, and you can reason exactly the same thing for a Z error on any of the qubits. A phase flip on any qubit within a block is equivalent to a phase flip on the corresponding qubit prior to the inner encoding, and that's actually pretty straightforward and intuitive if you think about how Z errors affect the 3-bit repetition code. So, one option for dealing with a Z error is to decode the inner code, and then detect and correct Z errors using the outer code, which is the modified version of the 3-bit repetition code that can correct for a Z error. So that corrects our Z error, and we could re-encode with the inner code if we wanted to do that. We can also correct Z errors in place, so to speak, without decoding and then re-encoding, and it's pretty straightforward, but to explain how we can do that, we'll need a little bit more space. Suppose that we decode the inner code, and then we compute the syndrome for the outer code using the same method as before, where we're only involving the 3 qubits from the outer code, and then we re-encode. Well, we can simplify all of these CNOTs just a little bit, and in fact we can use the relationships between NOT gates and CNOT gates that we just observed a few moments ago to help with that task. And by doing this, we can save 4 CNOTs, and this is the circuit that we obtain. If a Z error has occurred on one of the qubits, what the syndrome tells us now is not which qubit experienced a Z error, but rather which block the Z error happened in. But that's okay, because we know that it doesn't matter which qubit within a block experiences a Z error. The effect is the same for all 3 qubits within that block. And so we can in fact correct the Z error by applying a Z gate to any of the qubits within that block. This, by the way, is an example of what's called degeneracy in an error-correcting code, where we don't uniquely identify a given error, but we're able to correct it anyway. Finally, let's suppose that both a bit flip and a phase flip error occur, possibly on the same qubit. For example, let's suppose that a bit flip and a phase flip error happens on this qubit right here. As it turns out, these errors can be detected and corrected completely independently, and in fact it doesn't matter if we correct each block for bit flips first and then correct for phase flips, or if we do it the other way around. To see this, let's first observe that the ordering of these errors doesn't matter, so we can flip them around if we wish. The reason for that is not because x and z commute, because they don't. X times z is equal to negative z times x, but the negative 1 factor has no effect in this situation because it's a global phase. We can now move the z error just like before, and at this point it's evident that if we were first to correct each block for x errors, and then we corrected for z errors, we would then have corrected both errors. Alternatively, if for some reason we decided to correct for z errors first, we could do that, and the x error has absolutely no effect on that process. That has to be true because, number 1, the x error commutes with every single gate in the circuit that computes the syndrome for the outer code, and number 2, the ordering between the x error and the z gate that we apply to make the correction doesn't matter, just like we argued when the z gate was an error. So that allows for the correction of the z error, and we can then correct each block to eliminate the x error. So what we've argued is that we can correct an x error, a z error, or both on any one of the qubits using this code. In fact, we can correct for more errors than that, such as multiple x errors as long as they fall into different blocks, or multiple z errors as long as at most one block gets an odd number of them. But going forward, what will be most relevant is that we can correct an x error, a z error, or both on any one qubit. And in the last part of the lesson, we'll see how this is in fact enough to conclude that this code can correct for an arbitrary error on any one qubit. Before we move on to the last part of the lesson, in which we'll consider arbitrary quantum errors, we'll briefly consider the performance of the 9-qubit Shor code when errors represented by polymatrices occur randomly on the qubits. To be more concrete, let's consider a simple noise model where errors occur independently on the qubits, with each qubit experiencing an error with probability p, and with no correlation between errors on different qubits. The worst case scenario for the 9-qubit Shor code is that a y error, or in other words, both an x error and a z error, occurs on each affected qubit, and we'll assume this worst case scenario just for the sake of obtaining a bound on the code's performance. But you could also consider, for instance, that the 3 poly errors are equally likely. Now suppose that Q is a qubit in some particular state that we'd like to protect against errors, and imagine that we have the option to use the 9-qubit Shor code. Should we use it? Well, the answer is not necessarily yes, because if there's too much noise, or in other words, p is too large, using the Shor code could actually make things worse, just like we had for the repetition code when p is larger than 1/2. But if p is small enough, then the answer is yes, we should use the code. So let's see why this is and what it means for p to be too large or small enough for this code. The Shor code can correct any poly error on a single qubit, and in the worst case, where our poly errors are y errors, this means that the code successfully protects q with a probability given by the expression shown on the screen. Specifically, the code works when there are no errors, and that happens with probability 1 minus p to the power 9, because there are 9 qubits that must each be unaffected, and it works when there's exactly one error. And considering that there are 9 different qubits that could possibly be affected, this happens with probability 9 times p times 1 minus p to the power 8. On the other hand, if we didn't bother using the code, our one and only qubit would be unaffected by an error with probability 1 minus p. So the code only helps when the first probability is larger than the second, because these expressions represent our probabilities of success in the two cases, when we use the code and when we don't. Here's a plot of these two functions for small values of p, and we find that the break-even point occurs at about 3.25%. So if p is smaller than this value, then the code helps. At the break-even point, the probabilities are equal, so we're just wasting our time, along with 8 qubits, if we use the code, but otherwise there's no harm in it. And beyond that point, we should absolutely not be using this code because it's actually increasing the chance of an error on the encoded qubit, which we typically refer to as the logical qubit in this context. And that's happening simply because the chance of 2 or more errors on 9 qubits is larger than the chance of 1 error on a single qubit for values of p in this range. 3.25% may not seem very good, particularly when compared to 50%, which is the analogous break-even point for the 3-bit repetition code for classical information, but it's harder to protect quantum information. And moreover, although this code represents a brilliant discovery as the very first quantum error correcting code, and it happens to be great for pedagogical purposes, the fact of the matter is that it's just not all that good of a code in practical terms. So far we've considered X errors and Z errors in the context of the 9-qubit Shor code. Now let's consider arbitrary errors, starting first with unitary errors. So, for example, such an error could correspond to a very small rotation of the Bloch sphere, possibly representing an error that's incurred by a gate that isn't perfect, for instance, or it could be any other unitary operation on a qubit, and not necessarily something close to the identity operation. It might seem like correcting for such errors is difficult. There are infinitely many possible errors like this, and it's inconceivable that we could somehow identify exactly what error it is and then undo it. But we don't actually need to do anything different from what we've already discussed. As long as we can correct for a bit flip, a phase flip, or both, then we will in fact succeed in correcting for an arbitrary single qubit unitary error, and I'll now explain why that is. First, like all 2x2 matrices, we can express an arbitrary unitary matrix representing an error on a single qubit as a linear combination of the 4 poly matrices, including the identity matrix. And by the way, as you may have noticed, I'm using capital X, Y, and Z to denote the non-identity poly matrices, and I'll continue to do that for the remainder of the series. That's conventional in quantum error correction, and it also makes things a bit easier to read in this context. It's also going to be convenient to use subscripts to indicate which qubit a given qubit unitary operation acts on. So, for example, if we use Qiskit's qubit numbering convention, starting from qubit 0 on the right, then we have the expressions shown on the screen for various unitary operations on single qubits, where in each case we tensor the unitary matrix with the identity matrix on every other qubit. So in particular, we can express UK, meaning U applied to qubit K, as the same linear combination as before, except that each poly matrix is applied to qubit K. We don't need to bother with the subscript for the identity, by the way. The understanding here is that this is the identity on all of the qubits. Now suppose that psi is the 9-qubit encoding of a qubit state. If the error U happens to qubit K, then we obtain UK times psi, which we can express as a linear combination of poly operations acting on psi, which of course is just psi in the case of the identity. At this point, it's going to be helpful to observe that the poly Y matrix is equal to I times X times Z, so we can make that substitution in our expression. So this error has taken place, and now suppose that we attempt to correct it using the same procedure as before. The first step is to compute the syndrome, which in the case of the Shor code is 8 bits long. 2 bits for each of the 3 times we use the inner code, along with an additional 2 bits for the outer code, but it doesn't really matter. We can just think about it as some fixed length string. Here's a description of the state that we get just prior to the measurement of the syndrome, where each syndrome is whatever 8 bits we get from the corresponding poly error. Notice at this point that the two systems are correlated in general, and really this is the key to making all of this work. By measuring the syndrome, what we'll effectively do is to collapse the state into one where one of the 4 poly operations has been applied to the kth qubit of psi. And we'll know from the syndrome which poly operation it was, so we can correct it if needed. In particular, if we measure the syndrome and make the appropriate correction, then we obtain a state of the form shown on the screen, which critically is a product state. We have our original uncorrupted encoding as the right-hand tensor factor, which is what is most important here, and on the left we have a density matrix psi that describes a random error syndrome. But there's no longer any correlation with the system that we care about, which is the one on the right, because the errors have been corrected. At this point, we can throw the syndrome qubits away, or reset them in case we want to use them again, and that's actually pretty important, because this is how the randomness or entropy generated by errors is removed from the system. And that's how the discretization of errors works, at least for unitary errors. In essence, by measuring the syndrome, we effectively project the error onto an error that's described by a poly matrix. At first glance, it may seem too good to be true that we can correct for arbitrary unitary errors like this, even errors that are tiny and hardly noticeable on their own. But what's important to realize here is that this is a unitary error on a single qubit. And by the design of the code, a single qubit operation cannot change the state of the logical qubit that's being encoded. All it can possibly do is to move the state out of the space of valid encodings, but then the corrections bring it right back to where it was. Finally, let's consider what happens when an arbitrary, not necessarily unitary error occurs. The setup is the same as before. We've encoded 1 qubit into 9 using the Shor code, and some arbitrary error, represented by a qubit channel phi, occurs on one of the qubits. As we'll see, everything's going to work out in pretty much the same way as it did for unitary errors, and the first step toward verifying this is to consider a Krauss representation of our error. What we can do now is to follow exactly the same reasoning as for unitary errors, except that we apply that reasoning to the Krauss matrices rather than to a single unitary matrix representing an error. In particular, each Krauss matrix can be expressed as a linear combination of poly matrices, and this allows us to express the action of this error phi on whatever qubit k it happens to in the form that's shown here on the screen. All we're really doing here is to expand out the Krauss matrices as linear combinations of poly matrices. If we then compute and measure the error syndrome and correct for any errors that are revealed, we'll obtain a similar sort of state to what we had in the case of a unitary error. I won't go through the details. It's all quite similar to the unitary case, and also a little bit messier to write down, but conceptually speaking, it's pretty straightforward. I should mention that this all generalizes to other quantum error correcting codes, including codes that can correct for errors on multiple qubits. In such a case, errors on multiple qubits can be expressed as linear combinations of tensor products of poly matrices, and correspondingly, the different possible syndromes will describe corrections that are performed on multiple qubits rather than just 1 qubit, but the underlying idea is exactly the same. Again, by measuring the syndrome, we effectively project or collapse errors into a discrete set of possibilities represented by tensor products of poly matrices, and by correcting those errors, meaning the poly errors, we can recover the original encoded state. Meanwhile, whatever randomness is generated in the process is moved into the syndrome qubits, which we can then discard or reset, which is crucial because that's how the entropy generated by errors and syndrome measurements is removed from the system. And that is the end of the lesson, in which we've taken a first look at quantum error correction, including the 9-qubit Shor code and the discretization of errors. I hope you will join me for the next lesson, in which we'll discuss the stabilizer formalism, which provides us with a powerful tool for describing and analyzing a large and interesting class of quantum error correcting codes, including ones that are promising candidates for real quantum computers. Goodbye until then.